Okay, so as I was saying, that maybe you could get an A or a B or a C or a D or an F, or even withdraw from a course. Hopefully, not that. But you know, these are the distinct things that could happen. You can't get an A and a C in the same class. You can't get a withdraw and a B in the class, right? So these are disjoint events that partition a sample space. Exactly one of these things must occur. But maybe the event that you're really interested in is the event that you win the lottery. Okay, maybe that's this event in here. This is the event L. Okay, this is the event called L. Note that in this particular example, you cannot win the lottery if you get an F in a course. So don't get an F. Okay, it sort of screws you out of a chance at winning the lottery. Okay, don't fail. All right, so what I'm really interested in here is the chance that I get that by, you know, if I, you know, pick a point in this sample space at random, what's the chance that I get a point in L? I can write this as the chance of A and L plus the chance of B and L plus etc., plus the chance that I get a withdraw and L. See what I mean? And then so, you know, what this amounts to, if I want to write it with these conditional probabilities, is the chance of A given, it's the chance of L given A times the chance of A plus the chance of L given B times the chance of B plus so forth, the chance of L given withdraw times the chance of withdraw. Okay? And so that's kind of nice. It gives you a way to compute the chance of getting L based on, you know, these little disjoint regions here that make up L. Okay? That's what you're doing. You're just summing up all of these. You're summing up all of these pieces. Okay, so this is actually called the law of total probability. That's what that says. And that's essentially what we've done here. That's essentially what we did right here. Okay, just did an example. Now let's do something even more interesting. I think what you really want to know is, given that someone tests positive for drug use, what's the chance that they are actually not a drug user? Hopefully this probability will be pretty small, right? If you test positive for drug use, you know, if someone tests positive for drug use, then we want there to be a pretty high chance that that person is actually using drugs, right? Because we want this test to be a good indicator. We don't want to convict innocent people here, right? Well, here's what I'm going to do. First of all, I'm going to use the definition of conditional probability once to write this as the probability that the person is not using drugs and they get a positive test result over the probability that the test result is positive. That follows straight from the definition of conditional probability. Okay, you flip back to it in your slide there. Next, guess what? I'm going to use it again. I sure am. I can use it here. I can use it there. I can use it anywhere. I'm going to use it up here in the top. Okay, but what I'm going to do is I'm going to use it sort of in this sense over here. Okay, I'm going to write the chance of the intersection of two events as the product of a conditional probability and the chance of the other one. So I'm going to write this as the chance of getting a positive test result given that the person is not using drugs times the chance of the person not using drugs. See that? And then finally, for whatever reason, I'm going to make this look really super complicated. In the bottom here, I'm going to change this. I'm going to use this law of total probability to write this as the chance that the test result is positive, given that they're not a drug user, times the chance that they're not a drug user, plus the chance that the result is positive, given they're a drug user, times the chance they're a drug user. So this equality follows from the law of total probability. Okay. Now this looks really complicated, but it's actually pretty nice because what does this allow us to do? It allows us to actually compute the chance that someone's not using drugs, given that they had a positive test result. I can do this now. I know that the chance that the test is positive, given that they're not a drug user, is 1 minus 0.93, right, from up here. So the chance that it's negative, given they're not a drug user, is 93%. So that means the other 7% of the people who don't use drugs would actually test positive. Okay, so and then multiply that by the chance of them not being a drug user. It's 1 minus 0.007. Again, feel free to pipe up and let me know if I'm about to make a mistake. Okay, and then in the bottom here, hey, you know what? I've already done all this stuff. It was up here. It's the 7.623%. 0.7623. Okay, and what does that spell? 1 minus 0.93 is 7% times 1 minus 0.007 is that, and then divide all that by 0.07623. You get 0.9118. Holy smokes. Is that right? Gosh, that seems pretty awful, doesn't it? Look at what this says. Look at what this says. Given that the test is positive, what's the chance that they're not a drug user? 91%. Think about that. This, by the way, is called Bayes' rule, and it's applied all over the place. It's applied all the time. It's called Bayes' rule. Bayes' rule. Okay? It's Bayes' rule. Again, if you partition your sample space, okay, into a bunch of disjoint and exhaustive events, okay, whatever, you have n of them, maybe you're interested in knowing the chance of one of those events given some special thing, A, okay, that has occurred. You can write this as the chance of A given E1 times the probability of E1 all over the sum, the probability of A given E sub k times the probability of E sub k over running through that index k. It's exactly what we've written on this other page. Use conditional probability twice to get the numerator, and the denominator is just follows from is exactly the law of total probability. Okay, it's used all the time, and it often gets surprising results. I mean, really, I would think that if the test is positive, then there would be hopefully there's a low chance that the person is not using drugs. But in this case, it's like 90%. What is driving that? Geez, maybe it has to do with the fact that so few people are actually drug users. Actually, that's not true. I think these numbers are a little fishy. What this says that under 1% are drug or under 1% are drug users. So over 99% are not drug users. So these numbers can really be misleading. We should take a good hard look at that. Don't use drugs. Don't use drugs.